Welcome to the video introduction to Module 3. In Module 3, we will start learning about statistical inference, and in particular, we'll focus on estimation and confidence intervals. Recall that in Module 2, we learned about the basic cycle of statistics. There is a population that we want to learn about, but often the population is too large or difficult to collect data from for us to collect data from every member of the population, and so instead, we will never know about the entire population. Instead, we're going to draw data from just a sample. And then we're going to use the data from the sample to learn about the population. Statistical inference is the name that we give to the process of drawing conclusions about the entire population based on information just in a sample. Now, in last week's video, I said that a parameter is a number that describes a population, so it can only be calculated if we can collect data from every member of the population. A statistic is a number that comes from a sample, something we calculate based on sample data. And this is discussed more explicitly in section 3.1 of the textbook. So when we want to know about a population, we're going to think about that in terms of what number do we want to know, a number that's going to describe the entire population. And when we think about using our sample data to tell us about the parameters, we're thinking about calculating a statistic from the sample data to use as an estimate for a population parameter. I want to draw your attention for a minute to our notation. Notation is important for us to be able to know who and what we're describing. When we're describing a population, we do it with a parameter. When we're describing a sample, we do it with a statistic. So there's our who. And then what is it about that population or sample that we want to describe? That's our what. So we use the population mean, we use the notation mu, sample mean, x bar. Population proportion, we call it p. Sample proportion, we call it p hat. Population standard deviation, we give the notation sigma. Sample standard deviation, we give the notation s. And correlation, for the population, we give it the notation rho, and for a sample, we give it the notation r. This is important notation because it does really help, even though it seems more confusing sometimes to keep track of it all at the beginning, it actually makes things much more simple to understand when we start working with these things later on. So it may be useful to kind of jot this notation down and keep it someplace where it's easy to find until you get used to it, because it can be confusing until you get comfortable with it. Okay, so I want to give an example. A recent Gallup poll reported that 32% of Americans believe that animals should be given the same rights as people. Data were collected from 497 adults living in the U.S. So they're drawing a conclusion about all Americans based on data from 497 U.S. adults. So here the population of interest is all people in the U.S. and the parameter that we're interested in is P, the proportion of all U.S. adults, all Americans, that believe that animals should be given the same rights as people. Now, we don't have data from every single member of the population, so we don't know the true value of P. Instead, data were collected from 497 adults in the U.S., that's the sample, and a statistic was calculated, that's a sample proportion, P hat, of 0.32. And so what the Gallup organization is doing is estimating the proportion, the true parameter, P, the proportion of all U.S. adults who believe animals should be given the same rights as people, based on the sample statistic, P hat, of 32%. So this estimate, the single number estimate, the 32% in that example, is called a point estimate. We use a statistic as a sample as a point estimate for the population parameter, and it's just our best guess at what the population parameter is based on our data. But we have to remember that because the actual value of our point estimate depends on who ends up in our sample, point estimates will not match population parameters exactly. They're just our best guess given the data. Now, in the Gallup polls report, they actually report a margin of error associated with their estimate of 32%, and they say that their margin of error is 5%. And part of what we're going to be learning in the rest of this module is where does a margin of error come from and how can we calculate one? Now we know that point estimates will vary from sample to sample. So we're going to start off by looking at how they vary. So section 3.1 focuses on sampling distributions. Sampling distributions, we think of taking many, many samples from the same population and calculating the sample statistic for each of those samples. Then the sampling distribution is going to be the distribution of the sample statistics that we computed for different samples of the same size taken from the same population. A sampling distribution can be used to show us how the sample statistic would vary from sample to sample. And I'm going to start by looking at an example of a sampling distribution just to give you a sense of what we're really talking about. This is the population of Major League Baseball salaries in 2012, millions of dollars, and the mean salary for all Major League Baseball players in 2012 was mu equals $3.439 million. Now, let's look at how the sample mean might vary from sample to sample if we were to take samples of, say, 10 baseball players at a time. Now, I'm going to do this using StatKey. I'm looking at the sampling distribution for the mean salaries. I'm going to go in here, and I'm going to choose the data set that has the baseball salaries. And I can see that this is the same data set I was just looking at with a mean of 3.439. Now the sample size is set at 10. Let's suppose I take a sample of 10 of these 855 salaries. That particular sample had a mean salary of $2.037 million, which I can see here. And that mean is plotted on this distribution here. Okay, let's take another sample. Okay, so the next sample had a mean of 4.304 million for these 10 salaries. And that gets plotted and added to this plot. So now I've got two sample means plotted here. Let's take another one. Okay, we've got another 10 salaries. Ooh, this one came out with exactly the same mean that we had for the last one. Amazing. And it's added in as another dot on the plot. There, we've got another. Another. Let's add a whole bunch of samples. There's 1,005, 2,005. So now each of these 2,005 dots represents the mean calculated from one sample. And if I actually click onto one of those dots, it'll show me the sample from which it calculated that mean. So this gives me a sense of how my sample statistics might vary just by chance based on which players just happen to be ending up in the sample. Now remember, each of these means is a number, so I can describe this distribution in terms of its shape. You can see it's a little bit skewed to the right, but basically fairly mound-shaped. I can talk about the center. It's centered at the mean of 3.464, which notice is quite close to the mean in the population. And I can talk about how much variation there is from sample to sample in the sample means by talking about the standard deviation, 1.496. Now, in general, the shape and center of the sampling distribution are, the center is going to be centered around the true value of the population parameter, as long as the samples are selected randomly, and that's because random sampling is an unbiased method of sampling and is going to tend to give us a distribution centered around the true value of the parameter. The shape for most statistics we'll consider, as long as the sample size is large enough, the sampling distribution will be approximately symmetrical and bell-shaped or mound-shaped. One thing to keep in mind is that if a sampling bias exists, if you don't take random samples, if there's something about your sampling method that's biased, then your sampling distribution is going to be giving you bad information about the true value of the parameter. The center, in this case, of the sampling distribution wouldn't be at the population parameter because your sampling method would be biased. Now, the standard error of a statistic is the standard deviation of the sampling distribution. It's just a special name that we give to the standard deviation of the sampling distribution called the standard error. And we use SE in this course to abbreviate standard error. The standard error measures how much the statistic will vary from sample to sample, just by random chance. And this variability represents the uncertainty in our sample statistic, in our estimate. The standard error can be calculated as the standard deviation of the sampling distribution. A really important point that's going to be emphasized in this week's discussion board activity is that sample size is important. As the sample size increases, the variability in the sample statistics in that sampling distribution tends to decrease, and the sample statistics tend to be closer to the true value of the parameter. So you have a better estimate when you have a larger sample. For larger sample sizes, you'll see less variability in the statistics, so there's less uncertainty in your estimate. One set of sample means below was computed using sample sizes of n equals 50. The other was computed using sample sizes of n equals 200. This one's really asking which one is the sampling distribution based on larger samples, C1 or C2. So C1, remember, if we have more variability with a smaller sample size and less variability with a larger sample size. So when we have less spread out distribution like we have up here, that means that it's coming from a larger sample size. And here, down in the bottom with C2, we have a more spread out data set. So that's going to be associated with a smaller sample. So the answer here is B, that C1 is the larger sample of 200 and C2 is the smaller sample of 50. The variability goes down as the sample size goes up. In section 3.2, we'll learn how to understand and interpret confidence intervals. Let me give you a little overview. A confidence interval estimate, as opposed to a point estimate, gives a range of plausible values for population parameters. Instead of giving a single number like a point estimate, it's giving a range of possible values. One common form for an interval estimate is to express it as a statistic plus or minus a margin of error. So for example, in our Gallup poll example, 32% plus or minus 5% of Americans believe that animals should have the same rights as humans. Now, margin of error is a measure that tells us how much uncertainty there is in our prediction or our estimate. We can use the spread of the sampling distribution, which we called the standard error, to determine how large the margin of error should be for a statistic. Another key thing to keep in mind is that we'll come back to this more later, but the margin of error depends on a particular level of confidence that you want to have, that you're within that distance of the true value of the parameter. Usually we use 95% level of confidence when we calculate a confidence interval and a margin of error. Now, if the sampling distribution of a statistic is relatively symmetric and bell-shaped, we know from the 95% rule we talked about in Chapter 2, that 95% of sample statistics will be within 2 standard errors of the true value of the parameter. This gives us a way to make a 95% margin of error, which can be estimated using the margin of error equal to 2 times the standard error. So a 95% confidence interval could take the form of our statistic, or our point estimate, plus or minus 2 times the standard error. So when we make our confidence intervals, we start with a population that we're interested in. We draw a representative random sample from the population, and we use that to calculate our statistic. If I were to draw a whole bunch more samples, I could calculate statistics from all of those and create a sampling distribution. And since my margin of error is going to be 2 times the standard error, I could find the standard error by taking the standard deviation of that sampling distribution, multiply by 2 to get the margin of error, and then use that to get my confidence interval. When I want to interpret a confidence interval, keep in mind that 95% of all samples that I would take by random sampling would yield intervals that contain the true value of the parameter. So we say that we're 95% sure or 95% confident that one interval based on a single sample contains the true value of the parameter. So we interpret a confidence interval by saying something like, we're 95% confident that the true proportion of all Americans who believe that animals should have the same rights as people is between 0.27 and 0.37. The true proportion of all Americans who believe that animals should have the same rights as people, that is our parameter, and we're 95% confident that the parameter is in the interval. So in summary, so far, to create a confidence interval, we need 2 things. We need a statistic, like a mean or proportion, and we need a standard error of the statistic. And once we have those things, we can calculate a 95% confidence interval by taking the statistic plus or minus 2 times the standard error. Now, we need only one sample to calculate our statistic, but we need many samples to create a sampling distribution so that we can estimate the standard error. The reality of the situation is we are not going to take a whole bunch of samples. We only have one sample. So how do we create many samples from just one sample so that we can calculate the standard error? And the answer is we're going to create a population based on the original sample using something like a recycling technique called bootstrapping. And that'll be the focus of the last 2 sections of the chapter. So in section 3.3, you'll learn how to construct bootstrap confidence intervals. And bootstrapping is simply a technique that uses the original sample data in order to estimate the standard error so we can make a confidence interval. So hopefully this video will get you off on a good start to this module. If you find that you have questions, please post them to the help discussion board, and I will answer them within 24 hours. If you feel like you need a little bit more intensive help, send me an email and we can arrange a time to have a Google Hangout and answer some questions. Thanks, have a good day, and good luck with Module 3. Thanks.